My name is Dagem Haddis, and today I am going to present to you a biorefinery strategy that utilizes steam explosion and enzyme treatment for the co-productions of fermentable sugar, which is subsequently fermented to ethanol, and also a novel nanostructured material called cellulose nanocrystals. So due to the growing energy demand and the depletions of fossil fuel, the development of renewable energy is very important. And one of the renewable energy is bioethanol. So for producing this bioethanol, especially from lignocellulosic material by conventional methods, the feedstock must be broken down into sugar by the help of the enzymes, and the sugar is subsequently fermented to a bioethanol. However, depolymerizing this cellulose or this feedstock is very challenging due to the crystalline regions of cellulose. So the major challenges for the biofuel industries is, one, they use high enzyme dosage, and the process also requires a pretreatment in order to increase the surface accessibility of the cellulose to the enzymes. And this associated with a high cost due to the high cost of the enzymes. And beside that, the process takes a longer time. So in order to overcome such problem, we need to find an alternative approach. And one of the alternative approach is to produce a multiple product from a single feedstocks. For instance, if we observe the structures of cellulose, cellulose basically has an amorphous regions and a crystalline regions. So it's possible to convert the amorphous regions into fermentable sugars, and also it's possible to produce a novel nanostructured material it's called cellulose nanocrystal from a crystalline region, because this crystalline region is a precursor for the production of these cellulose nanocrystals. And these cellulose nanocrystals nowadays has a promising wide application in different industrial sectors because of its physical, chemical, and rheological properties. So what's the objectives of this experiment? The objective of this experiment is to develop a biorefinery strategy that co-generate an increased yield of cellulose nanocrystals and fermentable sugar, which subsequently fermented to a bioethanol. And the hypothesis of this experiment is a steam explosion treatment will facilitate the crystallization of semicrystalline by reorienting the cellulose molecule to form a new CNC precursor, which will improve the CNC yield during acid hydrolysis. And the enzyme treatment will hydrolyze the amorphous chain to a fermentable sugars. So the method that we follow is we followed an integrated method. So we combined steam explosion treatment with enzyme and acid hydrolysis. So the steam explosion treatment is responsible for the formation of a new CNC precursor, which will increase the CNC yield. And it's also responsible for to increase the surface accessibility of this cellulose to the enzyme hydrolysis. Then after that, we go to the enzyme hydrolysis, and during the enzyme hydrolysis, the enzymes degrade the amorphous chain into a fermentable sugars using the cellulase enzymes. Then we separate the fermentable sugars and undigested solids. So the undigested solids went to acid hydrolysis in order to produce a colloidally stable cellulose nanocrystals. So from preliminary result, we observed that the steam explosion treatment increased the glucose yield as compared to the popular wood, and at the same time, it also increased the CNC yield from 5.33% weight percent to 9%. So we conclude that from this experiment, steam explosion and cellulose treatment increased the sugar yield as compared to the untreated popular wood, and at the same time, it also increased the CNS yield as compared to, again, the untreated one. So in the future work, we are going to see the effect of this steam explosion pretreatment on the crystallinity of the wood, and we are going to determine also the effective cellulose loading that gives us the higher glucose concentrations. And we are going to identify an effective cellulose saccharification period that preferentially degraded the amorphous domains, and then we characterize the cellulose treated fiber and as well as the cellulose nanocrystals. So finally, it's time to thank my guiding lights. So I just want to thank my supervisor, Dr. David Bressler, for being very nice supervisors and for his support. or throughout all my research work. And also especially, I just want to thank Dr. Jack Sadler from University of British Columbia, and I would like to thank all the funding agencies, Natural Science and Engineering Research, Innotech Alberta, FP Innovations, Alberta Pacific Forest Industry, and Future Energy Systems. And finally, I would like to thank all of you for being here and for attending. Thank you very much.